Welcome to Life in Biology. I'm Dr. Joel Graff. This is a condensed lecture from my Principles of Living Systems class. It was our second day of class. I'm calling it lecture number 1, and we are learning some basic chemistry. So of course, to learn basic chemistry, it's handy to become familiar with the periodic table. We have rows or columns of elements, and each of these columns is considered a group. The groups have similar properties, and we'll talk about that later on in this lecture. We're going to talk about only elements that come from the top 3 rows of the periodic table, and the reason for that is that in biology we don't have to worry too much about the elements found down here, and that simplifies the chemistry that we have to deal with. So, in this lecture, I just decided to talk about some of the what some of the atoms would potentially look like in the top 2 rows of the periodic table. So here we're showing that hydrogen has 1 proton, helium has 2 protons, so its atomic number is 2. Lithium is atomic number 3, 3 protons, 4 protons, 5 protons for beryllium. Boron, 6 for carbon, 7 for nitrogen, 8 for oxygen, 9 for fluorine, and 10 for neon. I didn't bother mentioning how many neutrons these have. We'll save that for another time. But we wanted to take a look at what the electrons would be doing if the number of electrons equaled the number of protons. That is, we're dealing with an element with no charge. So we've got 1 proton in the nucleus, you've got 1 electron orbiting it. And if you go to a regular chemistry class, you're going to learn about electrons orbiting within orbitals that are of different shapes. But we're just going to use this Bohrs model of how to draw, I think it's Bohrs model of how to draw the electrons. So we've got our first shell for electrons, and there's 1 electron on hydrogen. For helium, there's 2 protons in the nucleus and 2 protons in the electron shell. There's only 2 elements in the top table of the periodic table, so there can only be 2 electrons in this first row of electrons. Once you get down to the second row of electrons, we're going to have 2 shells of electrons. With this first shell being full because it has 2, the third electron for lithium needs to go out onto the outer shell. Beryllium, 2 electrons in the middle, 2 electrons in the outer shell, and that matches the 4 protons that has. Boron, 2 electrons in the middle, 3 in the outer shell. Lithium, or carbon, I thought that was lithium because my handwriting's so bad. That's a C for carbon. 6 protons in the nucleus, 2 electrons in the first shell, and then 4 electrons in the next, for a total of 6 electrons. We've got 5 electrons in the outer shell here, 6 electrons in the outer shell, 7 electrons in the outer shell, 8 electrons in the outer shell. So it goes from 1 to 8, and there are 8 elements in that row. And so we're just slowly building our way up until we have the full outer shell like neon. So helium and neon are considered noble gases, and they don't do a lot of, there's no real reason for those guys to bother doing chemical interactions or chemical bonds because they're perfectly happy how they are. Their outer electron shell is filled with electrons. Fluorine, on the other hand, is not too happy. It would really like to have 8 electrons, but it only has 7. So we're going to see that sometimes you can pick up an extra electron for fluorine. In a similar fashion, lithium has 1 electron in its outer shell, and rather than getting 7 electrons to get to 2 full shells of electrons, it might lose that outer electron so that its outer shell looks like the outer shell for helium, which, remember, because there's just 2 elements in the top row, that's full. So the atomic number, we went over that. The atomic number is equal to the number of protons, and the number of protons is what defines an element. The number of electrons can determine whether you have an ion or not. If the number of protons stays constant, but the number of electrons changes, you can have an ion. We'll come back to ions in a second. We kind of talked about some of these elements at the far edge of the periodic table. Let's talk about some of the elements that are kind of in the middle. So for this row, carbon smack dab in the middle. It's got 4 electrons in its outer shell. It could gain 4 electrons or it could lose 4 electrons, but it actually comes up with a new idea. It decides to share electrons. Oh. Let's see, so let's give an example where you have a carbon in the middle, and then you want to surround it with 4 hydrogens. CH4 is the chemical formula for methane. It looks a little bit like this, although I'm drawing on a 2-dimensional surface, and it actually has 3-dimensional structure. But for now, we'll just deal with it in 2 dimensions. The carbon had 4 electrons around it, and the hydrogens each had 1 electron in its outer orbit. So when the hydrogen shares an electron with carbon, the hydrogen feels like it has 2 electrons because it's sharing those with carbon. This hydrogen would be quote-unquote happy, as well as this one and this one, because each of those is sharing a pair of electrons with carbon. Meanwhile, carbon feels like it has 8 electrons around it, because it had its original 4 plus the 4 that hydrogen's sharing with it, and so that molecule is pretty happy as it is. Now fluorine, if you take fluorine and you gain an electron, you get a fluoride ion. We changed the last letters, fluorine to fluoride, and that's just part of the going to an ion state nomenclature. And in that case, we've got 10 electrons and 9 protons. So its overall charge is -1. So let's take a look at some more ions. Sodium can be an ion, so can chlorine. So sodium chloride, we changed again. Chlorine changed to chloride, just like fluorine changed to fluoride, to indicate that we're dealing with an ion. That's your typical table salt. And the molecules here, the sodiums have given up an electron, so that they have a net, they have 1 more proton than they have electrons, giving them a positive charge of 1. Chloride ions, they took in an electron, but kept their proton numbers the same. If they changed proton number, it wouldn't be chlorine anymore. So you've got a chloride ion and a sodium ion. And these are held together with ionic bonds. We've got a positive charge and a negative charge, so they will form a regular crystalline array where you have a sodium ion, a chloride ion, sodium, chloride, sodium, chloride, sodium, chloride. And if I were to draw this in 3 dimensions, coming out from the sodium chloride here would be sitting a chloride ion. So it just alternates between sodium chloride the whole way through, and eventually, if you built up enough layers, it would have somewhat of a cube shape. So if you look at sodium chloride under a microscope, you'll see sodium chloride crystals are nice and square shape, and that's because if you were to break the crystal somewhere, it would break along one of these faces, so it would make a nice straight line between, say, these 6 atoms or ions there. Okay, and then I've already kind of mentioned it before, but these are held together with ionic bonds, and if you share bonds, it's called a covalent bond. So we're dealing with 2 different types of bonds at this point. Okay, now we're going to switch over to talking about some organic chemistry, and the simplest organic chemistry molecules are hydrocarbons. Molecules that contain carbon fall under the category of being organic. Not always, but if you're going to have an organic molecule, it's going to have some carbon in it. And then hydro stands for hydrogen. or is short for hydrogen. And so these molecules are made of nothing but carbon and hydrogen. We already took a look earlier at methane. It seemed kind of out of place at the time, but here's methane. We've got a carbon in the middle, 4 hydrogens outside of it. Everybody's doing some sharing of electrons so that everyone here is happy. This molecule is called methane. Meth being that it has 1 carbon, and ane doesn't make much sense right now, but we'll get there. This one is called ethane. So here we have 2 carbons, and they're held together with a bond. And then for those 2 carbons in this molecule, they each want to have 3 more shared bonds, 3 more covalent bonds. And so the hydrogen go ahead and fills up that outer ring here. So we have 2 carbons, C2, and 6 hydrogens, H6. So that gaining 1 electron brought up the hydrogen number by 2. This molecule is called ethane, eth for 2 carbons, and I might have said that. I'm just getting a little lost in what I've said versus not said so far. But going with the idea that meth means 1 carbon, eth means 2 carbons, 3 carbons is propane, 4 carbons is butane, 5 carbons is pentane, 6 carbons is hexane, I believe it's heptane, heptane. 8 carbons for sure is octane, and I think 9 carbons is nonane. So you can see by putting a different prefix in front of the suffix ane, you can indicate the number of carbons in your atom. So butane is the next one up. Let's have that be 4 carbons long. And then you go ahead and put hydrogens all around, and there will be 10 total hydrogens. And so that took a while to draw. We want to be a little bit lazier, so we could say CH3 to mention that this first carbon has 3 hydrogens associated with it. CH2, 2 hydrogens with the second carbon. CH2, 2 hydrogens with the third carbon. CH3, 3 hydrogens with the fourth carbon. So this one is a chemical formula of C4H10. But even this shorthand way here is takes too long to write out, so you can just make a squiggly line. Squiggle, squiggle, ignore the 7 and 8 for now. Squiggle, squiggle, squiggle. You have 2 ends, and you have 2 places where the line changes direction, and there's implied a carbon at each of those positions, at each end, and each of those 2 positions in the middle where the line changes direction. And you don't even need to put the black dots on, you can just do the red squiggle. I put the black dots on when I was giving the lecture because I was pointing out that at each of those places there is a carbon. How about those 10 hydrogens? They're implied. You just assume that if they don't tell you anything else, that there's going to be some hydrogens filling this out. So then, that is a 4 carbon molecule, and butane. But what about octane? It's 8 long, so we've got 1, 2, 3, 4, 5, 6, 7, 8. So you've got 8 different carbons indicated by this, and it's also assumed that you would have quite a few hydrogens all the way around this. Now, octane means that it's all single carbon bonds, or single bonds between each of the carbons. If you say octene, you would know that there's at least 1 double bond somewhere in that molecule. The double bond could happen between carbon 1 and 2, or maybe it could happen between 3 and 4. And what we do is we count the carbons, 1, 2, 3, 4, 5, 6, 7, 8, and we put, if we say it's octene, we would want to put a 1 in front of it to indicate that the double bond occurred right after that first carbon. If we have this molecule where the double bond occurs between the third and fourth carbon, it would be 3-octene. So it's whatever carbon gets followed by, or has the double bond connected to it, the lowest number is what you give that number. So ane means all single bonds between carbons, and ene means at least one double bond. We could draw that molecule so that it was a double bond here at the right side, and then all single bonds as you move your way left, and that would still be 1-octene, though. You wouldn't want to call it 7-octene, because if you flip this molecule end for end, it would have the double bond here, and then it would zigzag its way till you get to the 8th carbon. So this molecule here with the double bond at the far right side is exactly the same molecule as shown here with the double bond at the left side. So you wouldn't want to give these two molecules different names, like calling this one 1-octene and this one 7-octene. Instead, you would just stick with counting your carbons from what I would consider the most interesting end. Okay, so even if you have a molecule like this, the most interesting end is where this double bond is, so then you have to count your carbons from right to left instead of from left to right. And it appears that we've reached the last slide for this particular lecture. So this was an introduction to organic chemistry. The next lecture will be finishing up some more organic chemistry nomenclature.